Developing a model or working prototype is a crucial step in every definition of the engineering design process. These small-scale models are built to simulate the real larger objects or structures. Experiments are conducted on these prototypes to test how well they work and determine if the design is safe and effective before building the real size structure. It is much easier, safer, and less expensive to make design corrections on the model rather than the real object. Our task was to create a model which would serve to display the scale of the orbital ATKs, Antares, and Cygnus. This model contains a Cygnus payload of 17 feet standard configuration and 22 feet extended configuration, which you can see right here. It contains two Aerojet AJ26-62 engines, which with independent thrust vectoring liquid, oxygen/kerosene fueled, which is right here. The launcher diameter is 13 feet, and the payload diameter for both configurations is 10.1 feet. This is the launcher itself, but this is just the model. So here, this would be the diameter, and then right here would be the diameter of the payload. There were different ways to approach this problem. We could have built a rocket with random measurements. We could have taken the same size model, or we could have divided by a common number in order to reach a standard base size. We could have also scrapped the entire model and chosen to add different parts with different measurements to solve the problem. The benefits of the design were that the measurements were very realistic and they were compatible with my materials. The limitations of the design were that they were not exact, so I had to estimate the height of two of the measurements. I conducted experiments on the model by testing the flight affinity and the structural prowess. I learned how my materials were reliable for the prototype and the system dynamics were working properly, seen with my experiment. I modified the prototype based on the measurements that I originally had. I originally had random measurements, but when I was testing the model, it was not functioning properly. I decided to modify the design by making all the dimensions scale with the actual model. I was completely satisfied by my work and I learned a lot from this experiment. I was able to properly comprehend how to make a satisfactory model/prototype and learned that using the scale factor of the real design itself is the most beneficial to the functionality of the design. So here are all my values, which are circled. These are all my scale values that I used. And then to reach them, first I converted to inches the feet that they gave. So here they give 130 feet and 1,560 inches. I converted this to this by multiplying the feet by 12 to make this. Same thing I did with this one, the launcher diameter. This is the launcher height. Launcher diameter 13 feet multiplied by 12 makes 156 inches. These are related because this is this, but this is just multiplied by 10 to get this. So here I multiply by scale factor of 1/100 by the inches to get the scale factor inches. So my scale factor would be 0.01. Yeah, that would be my scale factor. So this is how I calculated my launcher height. I took the inches, multiplied my scale factor, and then this is how I got my scale launcher height, 15.6 inches. Same thing I did with this one, which is I took the 13 feet of the launcher diameter, multiplied by 12 to get the inches, and then I multiplied by scale factor of 0.01 and got the 1.56 inches. So I decided to use the scale factor of 0.01 because that was very compatible. It was very useful. I was able to easily reach this size using the materials I have. So using the materials I had, I was able to properly gauge which scale is best for me. And this is my model. I cut it open just so that you could see the inside Aerojet rockets and the payload. The Aerojets. And this is the model.